Hello, good afternoon. Assalamualaikum warahmatullahi wabarakatuh.
Good afternoon, Dr.
Scan this appendix. Can you try it? Is it okay or not?
Doktor,
Ya.
QR ni sama ke?
Oh, wah, lain. Atas untuk section 3, bawah untuk 4.
Thank you, Doktor.
The top one for section 3 and the bottom one for section 4. Is it working or not? Probably it's already expired. If it's not working, I'll try to refresh it again. Tak boleh. Alright, I try to reproduce again the QR code. It seems like it's my UTM is very slow. Wait, it's loading. Where is the QR? There is. Okay. Can you try again for section 1, the bottom for section 4? Sorry, section 3 and 4. Right, it's working. Still cannot. Which section? Section 3? 3. But your friend, yeah, some of your friends, 3 of your friends already. Three only. Alamak. Why like this? Problem. Okay, I will wait for another 2 minutes. Then if some of you got problem, then we just proceed. I will check your attendance by looking at the WebEx list after this session. All right. I need to close this for a while. If we have time during the break time, so you can scan it again, right? So okay. So my name is Herman. Okay, I will be your lecturer for this course. So before we go to the chapter, let me see some of the lecture information, right? Okay, can you see the slide?
Yes, Doctor.
Okay, thanks. Right, so you're in section 3 and 4. And basically, this is the group for the WhatsApp I've shared in the e-learning. If some of you haven't done it yet, so you can scan it now and join the group. I believe most of you have joined it. Okay, I give 1 minute. Right. So we move on to next one. So this is a little bit on myself. So this is my office, P19A, room number 050221. So this is my contact number. This is my emails, coordinator. It's my little bit on my educational background. Bachelor degree in UTM 2000, master degree in also in UTM 2007, PhD in Sydney, Australia in 2013. So a little bit on my working background. My requirements. After graduated in 2000, I've been joining this company, Panasonic, for in 2000 until 2005 as R&D engineer. And after that, I've been joining back to UTMs as tutor, followed by lecturer, senior lecturer, and currently associate professor. Right. So the timetables, I hope this is not clash with your timetable, tally with your timetable. Our timetable on Monday, supposedly this morning, 8 a.m. to 10 a.m. But I have a, a very urgent issue this morning. So in physically, we're going to meet at P19A BT7, Bilik Tutorial 7 or Tutorial Room 7. And also on Wednesday, 12 p.m. to 1 p.m., also at the same room, the P19A BT7. Okay, is it tally with your timetable? Right. Okay, good. Thanks. So basically, this is actually the continuing subjects for the another subject, prerequisite subject, which is 3133. So currently you are in 3143. So basically, you should take the 3133 first, whether you are passing that subject or fail. Never mind, but you have to take it first before you take this course 3143. Okay, because some of the fundamental and theoretical knowledge that has been learned before need to be used back in this course, right? So basically, the outline of this course is we start on learning the root locus, followed by learning going to use the root locus to design the PID controller, right? And then we're going to learn the time domain, the frequency domains approach. Okay, so previously you are doing the analysis of time domains in 3133. For example, you have learned on the first order system, the second order system, some of the performance characteristics such as the settling time, the rising time, the percentage of overshoot, the steady state error. So everything there is called as domains. Okay, approach which is frequency domains, where we're going to use mainly using the bot plots as the approach to do another design of controller, what we call as the lead, the lag, and lead lag controller. So basically, lead lag and lead lag controller is comparable with the PID controller. It has the same objective, okay, which is to reduce the error, to improve the transient response, okay, then to improve both of the things. So for example, proportional controller here is, no, the PI controller is comparatively similar with the lag controller. and the PD controller is comparatively similar with a lead controller, and the PID itself is similar to the lead controller. Okay, so never mind, don't worry about this. We're going to go into the details along with this course. Right, so we're going to have four course learning outcome. Okay, first of all is to design the PID controller in time domains using the root locus approach. Okay, as mentioned here is time domain analysis, time domain approach. The second one is to design the lead line compensator in frequency domain approach. Okay, and the third one is basically to see the skill of using the software. Okay, so we're going to use MATLAB here in order to solve for the designing of PID and also lead lag compensator, right? So we're going to evaluate your performance during the case study, right? And also CLO4 also coming from the case study, but we're going to see your skill of writing the reports, okay, in order to compile your results of the case study. Okay, so CLO1 and CLO2 is mapped to PLO5, CLO3 is mapped to PLO4, and CLO4 is mapped to PLO8. Okay, so I don't want to describe on this. Supposedly you should know everything here, what is PLO4, PLO5, and PLO8. Okay, so this is the detail. So this is our planning. We're trying to finish the chapter 1 basically for the root locus methods in 2 weeks, okay, in 6 hours, right? And sometime it be extended for another 1 or 2 hours, okay? But unfortunately, next week we're going to miss another 2 hours class, which is on Monday, because in Johor Bahru, basically, we have a holiday. Okay, we have a fall of Sultan Johor. Okay, so we're going to holiday on that day, on Monday. So in that case, I would like to extend it a bit on the following class on Wednesday. We're going to extend about half hour. Is it okay for you or not? Okay, because our class is 12 to 1, and we are currently doing it in online, and basically for the Muslim, there is no problem because we are in a fasting day. Okay, so probably we extend for half an hour. Is not a matter for you, isn't it? Okay, so yes, it's just to replace back the hours that we're going to miss on next Monday. Okay, thank you very much for the confirmation. Right. So followed by, okay, good, thanks. Right, finish on that. So followed by chapter 2, control system design via root locus. So basically, we're going to design check here. We're going to design PID, PID controller, and we're also doing the tuning of the PID controller here. Okay. Next, followed by mid-semester break on week 8. Okay. And after the mid-semester break, we're going to continue on chapter 3, about 2 weeks, right? So basically, we're going to study on the frequency domains analysis. Okay, so how we can use the bot plot to do some analysis of some parameters such as the phase gain margin, phase margin, checking the stability of the system by using the board plot method. Okay, and finally we're going to have a control system design via frequency response. So basically, here we're going to design this controller, lead lag, and also lead lag controller. Okay, so it will take about 6 hours on this particular chapter, and we have another balance about 3 weeks here, so you can make use this period to complete your case study, right? So, and basically at the final weeks, okay, the weeks 15, I will conduct what we call so-called as demonstrations. So basically you need I will add some things about how you use, for example, how you draw the board plots. Okay, so because I want to see your skill on using the MATLAB software to solve for the contents in this course, right? Okay, in terms of the assessments, we have 2 tests. Okay, test number 1 will give you 10%, and test number 2 will give you 15%, right? And we have case studies, 20%. So it's very big marks here. Okay, and another 5% for the quiz, right? So we have a quiz. Basically, the quiz is on just a chapter 1. Okay, quiz on chapter 1, and this is usual. Final examination are for 50%. Okay, so this is basically the schedule that we have set for the test 1, test 2, and also the quiz. Okay, so this is it's already fixed. Okay, we have set it 2 weeks ago after we have a meeting with all the lecturers, and we have booked the venue, and this cannot be changed. So you have to inform other lecturer, I mean, if another subject test is fall at the same time as what we have planned here. Okay, so test 1 will be on week 6, okay, 24th of April on Thursday from 5:30 to 6:30. Okay, test 2 is on week 13, 12th June, also at the same time, and the quiz is on week 7. Okay, so this is the following weeks after the test 1. Okay. So this after we have considered your the withdrawal date, where the due date going to be on week 8 normally. Okay, so we have to run the test 1 about 2 weeks before, so that we can have time to mark it, so you can have your marks, so you can decide whether you can carry on with the subject or you want to withdraw with the subject. All right, so previously we conduct the quiz on week 5, but at this time we change it to week 7 because we currently we have 3 weeks of online lecture, and then you back at physically week 4, and after that week 5, then you have to run the quiz. Then probably it is not comfortable for you, so we change it from week 5 to week 7, right? All right, basically everything I will say in the e-learning. So I'm only using or only managing the section 3 e-learning. Okay. So everyone in section 4, I have added into the section 3. But if your name is still missing from section 3, you can personal message to me so that I can add it in section 3 e-learning. Okay. So everything, including the notes, including the quiz, information about the sample of past exams, the marks, right? And sometimes I will put also the recorded videos on in the e-learning. Okay, so this is basically the reference book that we use. The first one is previously has been used, but currently I put it here as pending because we are currently doing some modification, okay, to improve quality of the modules. But we don't have any further information on this. I will inform you later on if the module is ready on the time when we are meeting in physically. Okay, so meantime, you can go to the reference books number 2. It's basically our main reference for this course. So basically about the outline of this course is for 3133 and also 3143 is taken from this reference books, Norman S. Nice, Control System Engineering. Okay, so the latest one is probably 6th edition. I'm not so sure if there's another later version for this. Okay, this is a standard one. You have to attend at least 80% of the class. Okay, in physically, you have to wear a suitable dress. Okay, don't make noise during the class and make full attention during the lecture. Right, that is a little bit on the lecture. Okay, some lecture info. Okay, we move on to, all right. So I would like to have a very quick recap on what we have done for another subject, 3133. All right. So we have, okay, so some outline here. We have basically what we trying to control. Okay, so we have two type of system. Okay, one is the man-made systems and another one is the God created system. So we cannot touch anything with the God created system because this is under God control. But what we can do is we can control the man-made systems such as this household appliances, another system, antenna, a rocket system, robot, and many things system that we can control. Okay, so we can control it by just putting some gain or probably an advanced controller such as a PID controller. We have the fuzzy logic controller from AI. We have neural network controller. We have advanced control for nonlinear systems such as the sliding mode controller and also H infinity controller. Okay, but in here we only focusing on the linear controller, which means that we are using the system that is a linear system. Okay. All right. So basically, with a control system, when we give an input, we have an output. So it's a very basic one. Okay, so for example, the input is the button when you're using the lift or elevator. Okay, you push the button, so that is the input. Okay, so you push the button, for example, to bring you to level 5. So the desired input is actually 5. Okay, the level 5, and the outputs, it's depending on how good of the system that we design it. Okay, so sometimes with a very bad system, even though we give the inputs of level 5, we're pressing the level 5, but some of the system will not giving you the correct level 5. So probably there's slightly higher than level 5 or lower than level 5, or sometimes it is not exactly at the level 5. It goes to the level 4, for example. So this is not a good system, not good design of a system. Okay, so these are example of system that are available by categories. For example, if we're trying to control the position, we have the robot arm, the crane system, okay, and so on. For the speed control, we have speed system of the aircraft, how we can control the speed of the washing machines, the climbing robot. And if we want to control the temperature, we have the air conditioning system, the heater, the furnace, and industrial system. Industrial control system, we have many systems that we can control. Right? If you still remember, we have the open loop control system, or OLCS. So this is the configurations. We start with the input or the desired, followed by the input transducer. So if you still remember, what is the function of the input transducer? Any one of you still remember what is the function of input transducer? You can type it, or you can voice it out. Anyone? To change what? Are you still with me? Not so sure, because when I projecting this slideshow, I couldn't see any other. Okay, yeah, you are still with me. Okay, so what is the function of input transducer? Okay, to change the physical parameter to electrical parameter. Okay, so for example, here the physical parameter is temperature. So we want it to be an electrical signal here. So that is the function of this input transducer, because the controller is only accepting the electrical signal, whether in voltage or in current. Okay, so we have to use the input transducer for this. All right. So before the process, normally sometimes it is embedded together here. We have the what we call as the actuator. Okay. So the actuator will change the information coming out from the controller, right? From the current or voltage information to become back to the physical information. Okay. So for example, we are using any one of you have any idea what is actuator? Example of actuator? I didn't hear or didn't see any message. What is example of actuator that you know? Okay, motor, good. So motor, we have valve. Okay, so this is mostly that we use. Okay, good, valve. Okay, so motor, we change the voltage that we give to the motor, and then the motor will drive the torque. Okay, so we can move something physically. Okay, or we can use the valve. We give the current to the valve, and probably the valve opening will open accordingly to the how much the current that been given to the valve. Okay, so it changed from the electrical signal to the back to the physical signal. Okay, as you can see here, we also have the disturbance. Okay, in the previous class probably we always focusing on this disturbance. So this disturbance, for example, if you use the cruise control system in your car, okay, so we set it at speed of 100 kilometer per hour. Okay, the speed is 100 kilometer per hour. So this is cruise control. Okay, by right, your car will drive at this speed. Okay, but due to some of the disturbance effect, for example, there is a wind effect, or probably the vehicle is climbing. Okay, so that is kind of disturbance that cannot be avoided. So probably if we are just using this open loop control system, this speed will reduce slightly, okay, to become 80 or 70. But if we are using the closed loop system, so probably even though we have this disturbance, for example, the time domains representation. So this is the speed, velocity. Okay, this is the time. We set it at 100. So even though there is probably a sudden wind, so probably there is a small change here, and it back to the original 100 kilometer per hour. So this is what we call as the regulation. Okay, we have two objective in control system. One is regulation, one is tracking, if you still remember. So regulation means the system will retain the current desired value, okay, into the what we want, okay, even though there is a disturbance coming in. And tracking is if we change the set point. Okay, for example, we want to use the lift system. We want to go to the level 1, level 2, and level 3. Okay, so probably this is the response for the first step. Okay, then when it goes to the second level, it gives this another response, and the third level it gives another response. Okay, so it tracks according to the desired input that we want. So this is the tracking. Okay, the tracking control system. The regulation is just now to remain at the desired reference signal that you want. Okay. Some other important keyword that we have seen before, the modeling. So we have done the modeling in transfer function. Okay, that is it. The transfer function, and we have another method which is what we call as the state space method. Okay, so this is the two modeling approach that we have learned before. right? Block diagram, we have learned how to reduce. If we have a complex block diagram connections, we can use the what we call as the block diagram reduction, and also the Mason rules. The Mason rules in order to find the simplest transfer function. Okay, just a single transfer function to represent the whole complex system. Okay, so this already what is pole, what is zero. So if we have a transfer function, the numerator is basically giving us the zero information, and the denominator will give us the poles information. Okay, the time response, for example, okay, so this is the parameter, or actually this what objective, yeah, the objective of the control system. So basically, we have three objectives of control system. We want to make the transient response as good as possible. We want to make the system as stable as possible, and we want to make the system as less steady state error as possible. Okay. So we take the very simple system. For example, we are using the elevator. Okay, so this, for example, this is ground level, level 1, level 2. So this is the cable to pull the cabin lift here. Okay, so if this cabin lift is moving too slow, so the passenger probably will feel impatient. The cabin lift is moving very fast. The passenger probably feel uncomfortable, and if finally, if it's reached at a certain level, it has an oscillation for more than 1 second, so the passenger will also comfortable. Okay, for example, like this. The first one, the slow one, probably it goes like this, very slow. Okay, to go to the level 1. This is ground level. Okay, so probably the passenger will feel very impatient. It's very fast. Okay, for example, it shoot like this, and then it come to the level. So probably it is very good, but sometimes it is for some people it's not uncomfortable on that. Okay, or if let's say it goes steadily, but finally it gives some oscillation before it goes to the steady state. Okay, so this oscillation is also uncomfortable for this kind of system, for the lift system. And in terms of the stability, so this system is basically stable because all the response giving us a stable time response. Okay, for example, we have an oscillation like this. Okay, most of the time when I am asking students if this system is stable or not, so your answer is unstable. But this is actually still in stable region, what we call as, anyone still remember what is this time response name? What is the name of this time response? We have two terms that can be used to represent this oscillation signal? Any one of you still remember? What is this? What's stable? It is undamped. That's undamped. But in terms of stability, yeah, good. Marginally stable. This is marginally stable. Or we can also use the term critically stable. Okay, critically stable. So this is two terms to represent this oscillation signal. Okay, in terms of the stability. And another objective is to ensure that the signal, okay, for example, this is our set point, the signal reach at the set point that we give, but sometimes the signal is reached at another level. Okay, so this is level 1. For example, this is only 0.8. So we have some error over here, what we call as the steady state error. Okay, so for the lift system, it's not good because yeah, the cabin lift will stop there. Okay, it is not reaching yet to the exact level 1. Okay, it's just 0.8 from the level 1. So we have some error over here. Or sometimes the lift goes exceed the level 1. For example, here is 1.4. Okay, so this is also not good. So we have to make sure that these three things is in the specification, suitable specification for the system. Okay, different system will have this different specification. For example, probably this error is not good for the lift system, but for a chemicals reaction system, is still in spec. Okay, it is acceptable, still acceptable. Okay, then we have to agree on that, right? Right. So this is the yeah. So if we relate it to with the damp, what is the name of this time response? It had some ripple oscillation here. What damp? Come on, come on.
Over them.
No.
Under them.
Yeah, under damp. Yeah, under damp. Okay. So next one, this is still under damp. Okay, this is still under damp, but the response a little bit slower than the previous one. This one is, what is this? Very, very slow. Yeah, over them. Okay, over them. Okay, and have another one? No, we don't have another one. Okay, great. So if we have, if let's say we have like this, it goes smoothly and just nice, meet at a certain settling time. This is what we call as critically damped. Oh, sorry, I have to connect with the charge, my charger. Oh, fan battery also low. still working. Right. So we have the critically damped here. We have it critically damped. Okay. We have under damped. We have over damped. What else? But it is not in the list here. We have undamped. Okay. So we have one over damped, followed by critically damped, under damped, and finally undamped. Okay. So if we relate with the damping ratio value, so the damping ratio is greater than 1, this is equal to 1, this is in between 0 and 1, and undamped is zeta is equal to 0. Okay, so I summarize all in this figure, right? So for the design step, first of all, we have the block diagram. For example, previously we have the schematic for the electrical system and also the mechanical system. And from there, we make the modeling. Okay, we do the modelings, whether in transfer function or in the state space form. Okay, and then we do the analysis, whether in time domain and frequency domain. So we have done for the time domain in 3133, and we're going to learn the frequency domain analysis in 3143. And then after we doing the basics analysis, so this is analysis without the controller. So this is without controller. Okay. So probably from our analysis, the steady state error is very big. Okay, for example, equal to 1. Steady state error is 5. Or the overshoot is probably greater than 30%. So probably we want to improve these overshoots and also the steady state error. So we have to use another approach, which is we design a stable controller that compensates all these bad parameters here. Okay. So what controller that we can use? For example, we can use the PID controller. We can use the state feedback, the intelligent controller such as the fuzzy logic controller, the neural net controller, the genetic algorithm, the particle swarm optimizations, okay, that all for intelligent control. And then we also have the lead lag controller that we're going to learn in this course. Okay, what time now? Shall we have a 5-minute break before we continue for chapter 1? Okay, we will meet at 3 p.m. Okay. Okay. For a while, probably I sharing back, but it's already expired. Generate it again. Not possible, but my UTM is already expired as well. Huh? Still there? Academic. That's attendance. Okay, you can take your break. We meet at 3 p.m. All right. So we continue. Okay. Sharing screen here. Can you, someone of you respond? You can see it. Okay, good. Thanks. So, so this is the real topic that we're going to learn, which is firstly we're going to touch on the what we call as the root locus. Okay, so what is root locus? Okay, before I continue with the root locus. Okay, why cannot? Okay, so I would like to summarize a little bit on some of the important focusing. Okay, so this is the outline of these topics. Okay, we start on the introductions, the root locus concept, the procedure on sketching the root locus. Okay, and finally how we can use the software, basically the MATLAB, to construct the root locus. Right. So that is what I'm trying to say just now. Before we go to the root locus, I have to summarize a little bit on the importance. So where is it? Divide by 2. So for example, if we have a second order system, so basically you're going to have a 2 poles. Okay, so where these 2 poles, we call it as, if you still remember this term, dominant poles. Okay, so this dominant poles is basically defined as the poles that are located near to this imaginary axis. So the 2 poles that are near to the imaginary axis is called as the dominant poles. Okay, so normally the dominant poles, we note it as SD. Okay, S means for poles location and D is for dominant, and normally we write it as negative sigma dominant plus minus J omega dominant. Okay. So for example, in here, in this figure, so negative sigma D is here, and we have plus minus here. So we have plus J omega D minus J omega D here. Okay, so for example, we have 2 plus minus J3. Okay, so meaning that this is the value of sigma D, this is the value of omega D. Okay, so the dominant pole also can be defined as in the damping ratio time omega n plus minus J omega n 1 minus zeta squared. Okay, so where this zeta omega n is actually sigma D, and omega n square root 1 minus zeta squared is actually the omega d. Okay, so that is for the dominant poles. So if we relate it to the settling time, Ts, so Ts is given by 4 divided by zeta omega n. So where zeta omega n is actually the sigma d. So if we know the value of sigma d, for example, here is 2, so we straight away can get the value of Ts, or settling time. Okay, peak time. Peak time is given by pi divided by omega n 1 minus zeta squared, right? So omega n 1 minus zeta squared square root is actually the omega d. So we have pi divided by omega d. Okay, so if we know the omega d value, for example, the location is at J3, so the omega d is 3. So we have pi divided by 3. Okay, so 3.142 divided by 3 is about 1 point something. Okay, second. Right. So if we discuss on the percentage of overshoot, it is given by exponent of minus pi divided by 1 minus zeta squared. Is it pi? Pi zeta, right? So, and multiply by 100. So this is the overshoot formula. So it is only related to the value of, so pi is actually fixed value, pi is 3.142. And the parameter is only the, okay, so it is where the overshoot is of zeta, or the damping ratio. Zeta is actually damping ratio, right? So if we have a relationship between the overshoots and also the zeta, so it is basically an decreasing exponent function. Okay, so for example, we have a zeta value of 0.5 over here, so we can estimate what is actually the overshoot value. So this is basically, if we put it back 0.5 over this formula, so we're going to have overshoot, for example, 20%. Right? So this is the summary of what we have learned before, because we're going to use back all this information when we are citing on the root locus method. Okay. So what is the root locus? The root locus is a powerful method of analysis and design for stability and transient response of the control system. Okay. So root locus is a graphical representation of the closed loop pole as system parameter is varied. What does it mean? Okay. So previously, when we have a closed loop system, okay, so we have a closed loop system. So this is the forward transfer function G. This is the feedback transfer function H. And normally we have a gain K over here, where we can vary the value of gain parameter here, okay, whether it reduce or increase. All right. So if we are considering only the open loop transfer function, so the open loop transfer function is simply given by when we open this here. So it is actually K, G, and H. K, G, H. Okay, so that is the popular transfer function. But if you are considering the closed loop transfer function, so it is actually given by, you still remember, for the closed loop, we are using this formula G1 plus GH. Okay, but in here, G is everything that is on the forward part here, which is including the K here. So in this case, we have Kg divided by 1 plus another G. G is also Kg and H. Okay. So if we have a real transfer function of G and H, for example, G is equal to 1 over S plus 1, H is equal to 1 over S plus 2. Okay, so if we substitute in this formula, so finally, the poles of the system is depending on the denominator part here. Okay, where in the denominator part, it is much dependent on the value of K here. Okay, so the value of poles cannot be immediately obtained. Okay, so we have to know first the value of gain K here. Okay, we will look into the example, few example later on. So what happened here? For example, we have a system with a gain K. For example, K is equal to 1. So the poles are located here. Okay, so that is for gain of 1. K equal to 1. What if we change to 2, 3, and so on, 10, 100? Okay, so if we change this K value here, so the closed loop poles here, so the poles at the denominator here will also change to a new location. For example, like this. It is a change in fact. Okay, also change. Okay, it is continuously change. Okay, according to the value of K. For example, just now, K here is for K is equal to 1, 2, 3, 4, 5, 6, 7. Just an example. Okay, for example, here is another combination here, K for 0.5. Okay, this is also 0.5, and this is K equal to 0.3, and this is for K equal to 0. Okay, we can see there is a pattern. Okay, if we connect all these poles location, the closed loop poles location, right? Okay, so finally we will have as a route. Okay, a route here. Okay, that we can call it as the root locus. Okay, this road here is called as the root locus. Okay, this is the root locus. If you remove all these poles location, then we just remain it as a line. So this is what the root locus look like. Thus, the root locus gives the transient response stations, for example, OS, TT, TS, the steady state error, and stability as system parameter is varied. So the system parameter mentioned here is basically we are talking about the gain K. Okay, so when we change the gain K, the poles locations also change accordingly in pair to the new location. Okay, so for example, For example, here at k equal to 6, when we use k equal to 6, then this is already in the right half plane where the system become unstable system. Okay, so this is when we choose k equal to 6. When we choose k 0 to probably 5 point something here, so this is still in the left half plane, so the system still stable. Okay, but if we exceed a certain value of k here, okay, a critical value of k here, so it moves to another region, which is unstable region. All right. That is the thing that I explained just now. Okay. This is actually a repeating from the one that I have explained just now, poles. So poles are given by the transfer function, okay, whether it is a open loop or closed loop transfer function, where we always look at the denominator part here. Okay, from this denominator part, it takes what is the roots from this denominator part. For example, the denominator is given by s cubed plus 2s squared plus 3s plus 2. Okay, so this is coming from here. Okay, so what is the poles of this system? Okay, the poles of the system is simply we equal it with 0, make it equal to 0, and then we solve for the what is the roots. Okay, what is the s value that can be obtained from this equation. Okay, so we're going to have 3 value of s, okay, because this is third order system. Okay, we have s number 1, s number 2, s number 3. So these 3 roots here, okay, this is what we call as the poles, because we are taking from the denominator part. Okay, so the open loop poles are easily found and they do not change with change the system, because if we referring back to the open loop transfer function just now, it is given by kgh, right? So even though we are varying the value of k here, for example, we have k s plus 1 s plus 1 s plus 2. Okay, whatever value of k that we use here, k equal to 1, k equal to 100, and so on, the poles is given by the same value. So the poles are -1 and -2. It doesn't change with the varying value of the k. But if we are considering the closed loop transfer function, okay, so it is given by, sorry, kgh kg divided by 1 plus kgh, okay, because the k is at the bottom here. So it will affect this function, okay, it will affect this function. Probably we have s cube 2s plus k plus s plus 2 plus k. Okay, so it's much dependent of the value of k. Okay, different value of k will give different poles location. Okay, So this, what does it mean by this statement? Okay, so back to here, what I have explained just now. So if we have kg and we have a feedback, so this is what we call as the forward transfer function together with the value of k, and this is the feedback transfer functions. So the open loop transfer function just need to open here, and then we're considering the multiplication of all this transfer function, which is k g followed by the h. Okay, so we have kgh. And the closed loop transfer function, we are using g1 plus gh. So the g is basically all this thing, g, which is kg, divided by 1 plus, again, g is kg, and h is h. So that's why we have this one. Right? So in general, of the G, the forward part just now, yeah, the forward part here, the G here, it could be equal 1 over S plus 1, S plus 2, okay? But simply in general, we take make it as N, or numerator of the G function, and the denominator of the G function. Okay. For the H here, we have another transfer function. Probably this H transfer function is given by 1 over S plus 3. Okay, so generally we represent it as the numerator part. Okay, in this case, the numerator is just equal to 1. So it is for H, and the denominator of H. What time now? Okay, all right. So these two forms, ng over dg, nh over dh. Okay, n is for numerator, d is for denominator. Right? So if we take it in total, so we have just now kg divided by 1 plus kgh. Okay, it's not here. This is the final one. We make it, if solve it, so we have k numerator of g divided by denominator of g, and divided by 1 plus k. G is numerator of g, denominator of g, times h, numerator of h divided by the denominator of h. This one, we multiply by dg and dh. So the upper part we got the ng, dg will be cancelled out, and we have dh over here. And if we multiply by dg/dh, this one will become dg/dh. Plus, if we multiply dg/dh, the remainder is k, ng, and h. This is what we found here. Okay, similar thing. Okay, so the transfer function of the closed loop system for the upper part is given by the numerator of the g function and the denominator of the h function. Okay, and for the bottom part, it's actually a combination of dg, okay, from the g function, and dh from the s function, plus k numerator of g and also numerator of h. Okay. Let's read example here. So we have G is equal to S plus 1, S plus 1. So let's say I write in a normal way, S plus 1 divided by S 2, and H is equal to S plus 3 divided by S plus 4. And again, K is K. Okay, find the open loop transfer function. So the open loop transfer function is given by KGH, HS, or KG S plus 2 times H is equal to S plus 3, S plus 4. Okay, so overall we have S plus 1, S plus 3, okay, S plus 2, S plus 4. Okay, so if you're taking the pole, so this is giving us the 0 value, and this is the pole value. Okay, so the poles from this open loop transfer is given by 0, -2, -4. So it always gives us this value, no matter what K value that we use. Okay, because the K is actually on top at the numerator part. Okay, if we change K to 1,000, 1 million as well, it doesn't change the pole's location, which is 0, -, and -4. So this is the open loop poles. Okay, but if we are considering the closed loop transfer function, so you have to form the closed loop transfer function, kg1 plus kgh, you substitute the g, you substitute the g, substitute the h here, and solve. And finally, you're going to have this transfer function. This is closed loop transfer function. Okay, so to take the poles location, we just look at the numerator, sorry, the denominator part. Denominator part. Okay, we are only check on the denominator. As we can see here, at the denominator, we found that it is influenced by the value of K here. Okay, so if we use, let's say we use K is equal to 1, so we have to substitute K equal to 1 here, here, and here. And finally, we form the function here to get the roots that give us the poles location. Okay, so that is for K equal to 1. But if we change K equal to 100, so it will give another poles value. It will be different. This pole and this pole for K equal to 100, K equal to 1 are different. Okay, because it affects this numerical function here, right? So that is what mentioned here. The closed loop pole is affected by K, and what we can say here, it cannot be identified immediately unless we know the value of K. Okay? If you know the value of K, then we can substitute over here, then we can find the poles location. Unless if the K is unknown, so we cannot identify the poles location. Okay, so that is the difference between the open loop poles and also the closed loop poles. Right, so probably I will take another 10 minutes. So let we introduce with the concept of root locus. Okay, let's consider this closed loop construction or configuration. Okay, so this is basically the G function, and the H function here, we don't have anything. So H is equal to 1. Okay, so if we consider closed loop transfer function, it is K G H 1 plus K, sorry, without H. So K G here is, sorry, it's not better to just remain it as G 1 plus GH, because G is comprised of everything that is here. Okay, right? So we have G is K1, K2 divided by S plus 10. That is for the upper part. And divided by 1 plus G. Again, we have K1, K2, S plus 10. And also multiply by H, which is equal to 1. Okay, so if we simplify further, so we're going to have K1, K2, and S10 plus K1, K2. Okay, or if you want to expand the denominator, so we have S squared plus 10S plus K1, K2. Okay, so this is what we have finally. And in here, the K1, K2 has been simplified as just a 1K. Okay, because at the bottom part here, we also do have K1, K2. Then this one also K1, K2. Then we can substitute as K is equal to K1, K2. So this is the thing. So now we have simply K divided by S squared plus 10S plus K. So this is the final transfer function of the closed loop. Okay. So the poles are related to the value of K that we use. Okay, let we make a table. Okay, let we use the K value here is equal to 0. When we use K equal to 0, then this one becomes 0. Then the on the S squared plus 10S. S squared plus 10S is equal to 0. Then we solve this one. S is equal to, this one can be simplified, S plus 10 is equal to 0. Okay, so S is equal to negative 10. Okay, so we have two possibility of value of 10. Okay, in this case, we only found a negative 10 over here. And for number 2, we consider as 0. Okay, let's we use K substitute with 5, S squared plus 10S plus 5 equal to 0. So if we solve this one, we're going to have basically two poles, because this is second order system. Then you can use your calculator to solve for this one. So the S1 is equal to negative 9.47 and S2 is 0.53 negative. This is the values. Okay, so on. You substitute with another value of gain, so we can have a complete table as given here, as different value of pole 1 and pole 2. Okay, what we can summary here, at the k is equal to 25, we can see that the two poles are located at the same location, which is -5. Okay, so if we draw it all the poles here, so basically we start from -10 and also 0. Okay, the initial point of poles when k is equal to 0 are -10 and 0. Then when we use k is equal to 5, we have a new locations, okay, which is just now negative 9.47, right? 9.47 and 0.53. So this is the second location of the poles, 0.53. It doesn't look yeah, 0.53. It's here because this is -1 and this is half. It is about negative 0.53. Right? So on. Okay, if we use k just now equal to 25, so the location are exactly at the same location, the two poles. Okay, poles number 1 at 5 and poles number 2 also at 5, -5, sorry. Okay, so this is actually the what we call as the breakaway point. So this is what we call later on as the breakaway point. Or we can say as a meeting point. This before it break, okay, to a different way. Okay, one goes to the upper part. Okay, so if you use k is equal to 30, we going to have this complex number, -5 j 2.24, and when use the same k, we also have the second poles, which is -5 minus j 2.24. Okay, so we have two parts, two location. One is at the plus, okay, the positive part, and the other one is at the negative part, 0.24. Okay, continuously. So until k is equal to 50, we have a different location of poles. So basically, this pole are paired with this pole, paired with this pole, paired with this pole, paired with this pole. Okay, at every change of k value, it has its own pair of poles. Okay, and normally it is symmetry between the top and also the bottom part. Okay, so if you look how it is moved, so basically it moves like this. Okay, so it moves just now. If you can swing back here, the pole is moving here, and poles number 1 is moving up. Okay, and if we are starting from here, the pole is going to the left, meeting at the 5 here, and it goes down. So in this case, we call it as we have two branches of the root locus. Branches. Okay, we have branches number 1, we have branches number 2. One is using this road, and the other one is using this another road here. Okay, so this is if you're still considering there are poles on the imaginary axis at the real axis here, and also another complex value here. So if we remove all those poles locations, so basically what we have here is just a way, okay? Okay, what we call as the root locus. Okay, so without the locating all those poles locations, this is what we have. The connection of the poles locations in a line. Okay, this is what we call the root locus. All right. Time now 3:44. Okay, that's another half one slide here. From the root locus, what we can conclude for K less than 25, the poles are all the real poles, meaning that all are located at the real axis. Okay, so just now, if I draw it again here, it started from here and -10. So before K is equal to 25, where the poles are -5 here. So this is K 25. This is K equal to 0. K equal to 0. When K is less than 25, so all those poles are located along this real axis. Okay, so if we relate back to the theory that we have before, if the poles are located on the real axis, this is considered as overdamped system. Okay, because at one time there are two poles located on the real axis, so this is considered as overdamped system. When K is equal to 25, so this is overdamped. So when K is equal to 25, so we have two poles that is located at the same location at -5. So this is what we call as the critically damped system. Not critically stable, critically damped. Okay. And when the K is greater than 25, means that all those poles are now located on the complex number. Yeah, whether to the top or to the bottom part. Okay. So all this call it as an underdamped system. All right, because all poles, because at one time the poles should be like this. Okay, this is become like this because we are considering many gain here. At a certain gain, only two pair here, only one pair, which is comprised of two poles, right? So we call it as the underdamped system. For the underdamped system, regardless of the gain value, the real parts are always the same. Okay, as we can see here, the real part here, which means if we have just now from the table, the real value all are similar value, -5. Okay, whether it goes to upper part or bottom part, all at the -5. Okay, so meaning that at any value of gain, just now we up to 50 gain, but if we increase again, K equal to 1000, the root locus we're going to the extending at the straight line here, okay, without crossing this imaginary axis. It goes like this, it's perpendicular, okay, it will not crossing this imaginary axis. So most of the time, this system will be a stable system because it's not going to the right half plane. Okay, it's always at the left half plane. Okay, so that is what mentioned in this statement. Since the root locus never cross to the right half plane, the system is always stable for all value of k. If k is equal to 1 million, okay, 1,000. Okay, so all the condition of this k will give the stable system. Root locus is useful for higher order system. So we're going to touch on the higher order system on the next lecture. All right, that's it for today. So anything has been covered basically, but for the root locus, it's just a few. We more on the revision today. Okay, is there any question? Before we dismiss, is there any question? Okay, thank you. So without further ado, we dismiss this class. We're going to meet again on this Wednesday, 12 p.m. Okay, thank you very much, class. Wabarakatuh. And very good day. All right. How to stop this one? Okay, thank you. Welcome. Why not stop me? Where is the button? Okay, welcome. Stop sharing. Right, and then end meeting. Okay, thank you very much.